Okay, anybody just recently joined, it doesn't have ability to record? Okay, Randall, I think you have permission allowed to record files, okay. Okay, so we're gonna do PSpice today. So somebody please open up Sassafras or however you go in and you can run the simulation's pretty easy today. Amir's been doing it a few times. If one of you other students want to have the take over the wheel, yeah, please open up and volunteer. Otherwise, yeah, Amir will probably step in and do it again. Okay, anybody else new who joined who needs to record? Okay, I'm going to start then. Let me minimize this for now. Okay, this lab report's marked up for the analog discovery. So this is a single supply op amp circuit. It's a non-inverting amplifier. And yeah, this is really just getting more practice working with op amps and characterizing them and so forth. So this is our circuit here. So we'll talk a little bit about that first. So again, it's a non-inverting. So the signal is actually going to come in here right to pin 3. There's a circuit they have on the next sheet. It says connect to VN. And then here is VN. So when we connect the signal source, and we'll do this in Spice, we'll use a capacitor to isolate it, because a signal source will generally have like a 50 ohm output impedance. So anyway, our circuit looks like this. So we've got pin 4, which in the past we tied to minus supply voltage. We're going to connect that to ground, and then we're going to connect VCC to, on the analog discovery, we got 5 volts. And that's the highest we can get. So now what we're doing here, this little resistor divider, this creates like a 2.5 volt reference voltage, VREF. And what's going to happen is our output, when we do our transient, we'll see this, it's going to ride on whatever voltage we set here. So we'll set it midway between 5 volts and ground. And then the signal, the sinusoid or triangle or whatever we use, will ride on a 5.5 volt DC offset. So how do we get away with that? Well, this capacitor here is really important. So normally, if you remember an inverting amplifier, it doesn't have these elements here. You basically drive into pin 3. And then this resistor is normally just connected directly to ground. Now we put this capacitor in here, and it's a blocking capacitor. It blocks DC currents. So as far as the DC is concerned, we're going to have 2.5 volts DC here at VREF. And then we're going to have 2.5 volts at VN, because this is a very high impedance. There's not really going to be a voltage drop in this direction. This, I mean, for all practical purposes, this is going to be like 10 mega ohms or something like that. So it's much larger than this. And so we're not going to have a different voltage there. But again, the magic of op amps, you have a very high impedance here, but you essentially have the same when it's in its operating range. When you have the 2.5 volts here, you're going to have 2.5 volts here. So you're going to have the same voltage at both of those nodes. And as far as that 2.5 volts, there's not going to be any current going this direction because the capacitor blocks it, DC currents. So if we have 2.5 volts here, we're going to have 2.5 volts here. And so the 2.5 volts isn't going to see this resistor ratio and it's not going to be amplified like the small signal or the AC signal we're going to apply. So that's fundamentally what's going on here. So the first part of this lab, the first part of the pre-lab, It says, shows the operational amplifier configured in a non-inverting amplifier, operate from a single supply, and I marked that up as 5 volts. The default specification is using, in the lab at the school, we use a 741. That's a very old op amp. In your kits, your analog discovery kits, you have an op 37, or there's an op 27. You can use either one of those. These are much better devices. These are designed, I don't know. The 741 was probably designed in the 1970s. Well, it was designed in the 1970s. And this is more modern. This is probably designed maybe 20 years ago. And it's just a much better device. It's more balanced. It has much better performance. Okay. Let's see. Okay, it talks about a potentiometer to provide a DC bias voltage at RF. We don't need to use a potentiometer. They're kind of difficult to use. The ones in your kit have really tiny wheels on them, and they're difficult to. You need like a little special screwdriver to turn them. So a potentiometer, though, is basically a variable resistor, or you can even think of it as a resistor divider. So you could put 10 volts here, or 5 volts here rather, and like if this thing was like a 10K ohm resistor, what it allows you to do is basically move the contact point between 10K ohms and 0. So if you have it midway, essentially you have 5K on this side and 5K on this side, and you've divided that voltage to 2.5 volts. Okay, so that's how a potentiometer works. So it's basically a resistor with a wiper, or swiper, we call it, where you can control the resistance relative to this point and this point. In our lab, we can just simply do two things. We can use either a resistor divider, like we could use a 5K and a 5K, or a 10K and a 10K, and put those on either side, and then just bring the mid voltage. So if I have 10K here, 10K here, I have 5 volts here, I got 2.5 there. That's one thing we do. Or the analog discovery has 2 power supplies, so we could just use the secondary supply when we build this. Today, when we simulate it, we'll just use a resistor divider here to represent the potentiometer. Okay, so looking at the pre-lab, I was just writing some notes before I came on. Again, here's our circuit. And I said you can use either a resistor divider or the second supply of the 82 to create this voltage. So in our lab, we can also use a battery there if we want to. On the simulation, we could use a 2.5 volt battery would work as well. But the idea here is that, you know, if you were to implement this circuit, you know, this could be like an audio amplifier for like a microphone or headphones or something like that. If you were to implement it, you don't want to have a bunch of different voltages, but different supplies, like DC to DC converters create 2.5 and 5. So what you would do is you'd make this one 5, and then you would just use the same voltage supply here and just make a divider to make this reference voltage. Okay, now the first question is, or the first part of the pre-lab is you want to prepare a gain to be somewhere between 30 and 45. So these are different resistor ratios. Like if you used 68K for R2 and 30, no, that's not 30K, I'm sorry. 2K, 2.2K, 2.2K for R1, you would essentially have like a gain of 34. Or yeah, 68 divided by 2.2. Let me do that. 68 divided by 2.2 equals, you'd have a gain a little bit over 30. It'd be 30.9. So another way you could get that kind of gain would be 47 over 15. 68 over 15 would give you a gain of 45. And then 100 over 2.2 would give you 45. So once again, the instructions say design the ratios so that you can get a gain between 30 volts per volt and 45 volts per volt. So any one of those resistors will work. Okay, so the second part of the pre-lab, it says, at what frequency is the reactance of the 10 microfarad capacitor, that's this one here, equal to the magnitude of the resistance R1? Call that frequency FP1. This is the pole frequency of the transfer function for the signals. Okay, so this is going to be like the dominant pole that's going to determine when the amplifier really turns on. So like at DC, this thing isn't providing any gain, but as you go up in frequency, this essentially becomes a short circuit, and then the amplifier just becomes a normal non-inverting amplifier. But that the combination of this RC, these RC values will determine what frequency that amplifier will turn on. So for the math there for that question, if in my case, I use 2.2 K ohms for R1, and then 2.2 K ohms is equal to 1 over, and this is the impedance equation for a capacitor, 1 over 2 pi f, or 1 over radial frequency times C. I'm sorry, 1 over 2 pi f C, or 1 over the radian per second frequency of C. So I got FC1 is equal to 1 over 2 pi times 2200. That's the value of my resistor. And then a 10 microfarad cap. So I got 7.23 hertz. And now step number 3 in the instructions, it asks, if Vref equals 2.5 volts, what are the DC voltages at V out and V2? So once again, going back here, whatever voltage we have here, we should see at this node, and this node. And it shouldn't be amplified because there's no DC current flowing in this direction here. So it's just going to be voltage traveling all across all these high impedances. Okay, and then the fourth question is, later in the experiment, an AC signal will be connected to Vn in addition to the DC bias portion of Vn. Thus, at the input Vn, both DC and an AC signal will be applied. This step checks the input resistance at that node. Assuming that the operational amplifier's input resistance is infinite, what are the lowest and highest small signal resistance to ground? Okay, so if we use the potentiometer, when you have the potentiometer here or here, it's essentially a connection to ground. Because remember, a power supply, a DC power supply, the output stage has very big capacitors to filter any noise. So from an AC standpoint, DC power supply looks like essentially a short to ground. Now, in this simulation that we're going to do, let's use two 10K resistors to create a voltage of 2.5 volts. So I've got essentially a 10K to ground and a 10K to the power supply. And those are essentially in parallel, because again, that's from an AC standpoint, that VCC is a ground. So I got 10K parallel to 10K equals 5K. So my largest resistance would be 27K. Now, if we were to actually use a potentiometer, if the wiper is over here at ground, or if it's all the way over here, the question was, what's the lowest resistance? And that would be this 22K ohm here. But in our case, we're going to use 27K. And so now when we connect in the lab instructions, we're gonna put a signal source out here, and then a capacitor is going to isolate that and connect to this point here. We can use another 10 microfarad cap. So that's going to create another pole. And so I got FC2 is equal to 1 over 2 pi times 27K times 10 microfarads, and I got 0.58 hertz for that. Okay, so those are the pre-lab calculations. So let's jump in. There's in the SPICE simulations, we basically build the circuit, look at the DC operating point, and then we do an AC sweep, a transient, and I think that's basically it. Yeah, that's basically it. So who wants to, I'm going to stop sharing. Who would like to run the SPICE today?
I have it up if no one else wants to do it.
Oh, good. Yeah. I like Amir to do it, but let's give somebody else a chance. Okay. So yeah, let's go. I'll Let's see if you can take over the screen. Oh, good. You already opened it up. Okay, does
Yes.
anybody need any review about opening PSpice, or are we good at this, starting at this point? Speak up if you want us to go back and show you how to get into this point. Okay, then let's proceed. Okay, so let's go to your components. And we'll need let's see, we'll need 4 resistors and 2 capacitors and an op amp and a couple yeah, power supplies. Yeah, so let's put a couple in line like that. 2 of those you can rotate. Let's rotate R3 and R4.
All right.
Okay, and let's put R3 and R4 to the left. R4 underneath R, yeah. Let's put R4, just put them in series to the left, and we'll use those to create our 2.5 volts. So you can put R4 underneath R3. Good. Okay, and then we'll need some capacitors. Those can be in a horizontal configuration. So let's get 2 capacitors on here. Yeah, put those left of put one left of R one.
Okay.
Yeah, and now put the other one. You can put it like just to the right of R3. I think that'll be okay for now.
Oh, what's happening?
Schematic is yeah.
Won't let me drag this one. Oh, there we go.
Yeah, there you go. Okay, now let's go look for the LM74, or no, let's see. We can try. Let's see if we can find an OP27. That's what you have in your kits. So let's go to the component, and we might have to load a library. Let's look for that real quick. I forget if that's there. So that little component up in the upper right-hand corner. Yeah, click on that. And oh, I see OP27, huh?
Yeah, I was about to ask you if this was the right way.
Yeah, let's try
do
that.
it.
I thought
Okay.
we had to load an op amp library. Let's see what comes in.
Just a regular one or one with like suffix? There's like
Um,
A, B, C, E, F, G.
let's try the regular one and see what happens. Okay. So,
Not quite.
well, maybe that plus on the top, I'm guessing those are the power supplies. Let's bring in one of the other ones that you have there too, and let's see
Okay.
what we have. You want to try let's try A and see what that one looks like. I don't think I've used these before, so okay, so they're all essentially the same.
Wait, how did you get the op amps?
Oh, there's a library. Let's see. I think you have to go up to library up above.
It's like place part, I think, right?
Yeah, but sometimes you have to load a library. So let's just review that. See, where there's a, okay.
Oh, right here.
Yeah. See that little green box? Yeah, that one there. You open up that. If you want to go find op amps, now scroll down and there's like, these are ORCAD libraries. And then scroll down to the O's and you should find one that says op amp. So there's all sorts of stuff in here. There's logic gates and things like that. We're getting close to
Amp.
yeah. Click on that. So that's in your thing now. Now just type in OP27 there and see what okay.
Oh, I see it. There we go. This one.
Yeah. See if it's let's see if the model's any different. Oh, let's use this model.
Okay.
I have a feeling we're gonna have better success with that. Okay, because it looks very much like the LM741 model. Okay, good. Yeah, place it right about there. Okay, now we need we need a DC power supply. So let's put in VDC. Yeah, you can put it
Um,
right there.
Okay.
Okay, so let's hook up a few things and see where we're at. Okay, so the bottom of the DC power supply, you connect to ground. And just under the balloon, yeah, that's right. And then the top will go to pin 7. Okay, good. And now the pin 4 will go to ground.
I just hook it up down here.
Yeah.
Okay.
And then R2 on the right side will go to pin 6.
Oh, I misclicked. There we go.
So we're not going to use pins 1 and 8. Those are to like off tune out any offset voltage if you need to. Okay. And now let's see. R1 will connect to R2 in between. And then that junction node will go actually to pin 2.
Okay. It's a little crowded. Mind if
Yeah,
I
you
move
can
these?
you can move things
Okay.
around. Yeah.
There we go. And then this junction's going to
Pin 2. Good. Okay. And then C1 connects to R1. And then the other side of C1 connects to ground. Might want to move. Yeah, okay, that'll work. That'll work. Okay. And I think we can move, let's move R3 and let's move R3 and R4 inside that little box you've made there. Yeah, and then C2
Okay.
can move outside. Or actually, C2 is going to connect to pin 3. So actually it was pretty good where you had it. Things are getting a little
Okay.
crowded. But
Yeah.
so let's put a wire between C2 and pin 3. We might want to move the op amp, the whole thing over to the right a bit. Yeah, that's good.
Okay. I'll just move this inside here.
Yeah, that'll work.
Okay.
Okay, and we're gonna put let's move C4 and C3 down too. So move them below C2. So you can move R4 to where it touches the ground.
Okay.
No, just to the line. Just go down vertical.
Oh, my bad. Right here.
Yeah. And then let's move C3 to where it touches that one. Oh, we're actually going to need another resistor in there too. We're going to need one more horizontal resistor. That's going to be 22K.
Type in the whole thing.
I don't know if you need to do that. I'm not sure. Okay, so we're stuck in the op amp library. See over there to the right. Yeah.
Yeah.
Select analog. Okay.
There you go.
Now type in R. Yeah.
Oh wait, that's right here. Whoops.
Yeah. Okay, so put it at the junction of R3 and R4. So put it like at their midpoint.
Right here.
Yeah, that's a good spot there. Okay. Okay, so now we'll make a wire from R5 go to the top of R3 is going to connect to your power supply.
Okay. Wait,
So-
which?
So you can loop it up and over the top.
So like up here.
No, move R3 down. Yeah, move it close to R4. It was good where it was before.
Oh, okay.
Okay, that's good right there.
And then what do I do with R5?
Okay, so the one end, the right side of R5 will connect to pin 3 of the op amp.
Oh, okay.
Other side, other side, other side of the cap. Yeah, there you go.
Oh, oops. Oh, there we go.
Okay, good. And then that the other side of R5 connects to the junction between them. Yeah, that's good. And now the top of R3 connects to your VCC. So you might want to just squirrel that out over the top. So maybe come up vertical. Yeah, that works.
Right here.
Yeah, that's good. Now let's move the whole circuit to the right a bit. Because you got it. Now we have to put an AC source in there as well.
Oh, okay.
Single source. Yeah, just yeah. Good. Okay, that's good. Okay, so let's put in actually we'll put a sinusoid. So let's put in a V sign. So you might have to click on source on that. Oh, is it good? Okay, good. There you go. Yeah, put that there. Yep. So one of that's good. Okay, so C2 connects to the top of that. And then,
Okay.
yeah, so you can go just straight across, good. And then the bottom connects to ground. Okay, I think we have everything here. So let's just go, we'll do the resistors first. So let's go to R1. Let's, in the kits, we have 2.2K ohms. So let's make that 2.2K. Good. And then R2, let's make that 68K. So that'll give us a
68K.
gain. Yeah, that'll give us a gain a little bit over 30. And actually, because we have our analog discoveries, we don't have a lot of dynamic range. So it probably is best to keep the gain on the lower end of the spec. So anyway, that's all good. V1, we can make that 5 volts. You're to the right there, yes. We're not going to connect pins 1 and 8.
Okay.
Those are used to tune out an offset if you really need a real precision circuit, but we're good with what we got.
Mhm.
Okay, so C1, let's make that 10 microfarads. That's the other. Yep. And while we're at it, we'll make C2 10 microfarads too. C2. Oh, you know what? I just remembered something. Some of you, I still need to send components out, capacitors and resistors and things like that. I forgot all about that. Some of you who already had 82 kits. So I'll make put that on my list for things to do tomorrow. So I'm sorry. Well, actually, we'll build next week, so they'll get there in time. So let me just write a note to myself. Send components. Okay, good. So we got 10 micro, 10 micro. Let's make R5 equal to 22K. And then let's make those a little bit bigger. We'll make them both 10K.
Okay.
You don't need a lot of current there. So I'm thinking that, you have less current. You're dissipating less current. Okay, everything's looking pretty good here. Okay, so the first thing it wants you to do is to see the bias or operating points. And if you look up in the window there or on the command bar at the top towards the right, there's one that's dark. It's got like a line. Yeah, that one there.
This
So
one?
that enables the bias voltage display. So we want that one on.
Okay.
Yeah, click it again. So it was on, I think, already.
Oh,
Okay.
okay.
And then the next one is if you want to look at current and power. But for today, you can click that on. Yeah, well, let's click on current and we'll just see what's going on there too. We'll turn it off after we run it. Okay, now what I have found is there's like a bias point simulation, but I find it's more effective if we run a transient simulation, and then all those voltages will pop up after you run it. So let's set it up now to run a transient. Oh wait, I'm sorry. We got to set up a beat. Yeah. So offset is equal to amplitude. Okay, so this is a lot of gain. So we're gonna make our amplitude, okay, offset 0. And we're gonna make our amplitude 50 millivolts, and that'll give us like a signal that's 100 millivolts peak to peak. So 100 millivolts peak to peak times 30 will give us a 3-volt peak to peak signal. And so we only have a 5-volt headroom, so we may have to actually bring that down. Oh, I said 50 millivolts,
Oh.
50. And we'll see how that works. We may actually have to back off on that. Okay, so frequency, let's make that 10 kilohertz. We want to make sure that that C1 is fully turned on. So 10K is good there. You don't have to write hertz.
Oh,
In
okay.
fact, sometimes Spice, I forget which, but sometimes it actually gets confused.
Yeah,
You
that's
put too
yeah.
much information. Okay, and then AC equals 0. Okay. Okay, now let's set up the simulation to run a transient. So we have a 10 kilohertz frequency. So if we run, okay, 1/1 kilohertz is 1 millisecond. So if we run 0.5 millisecond duration there, good time to main transient. If we go for 0.5 milliseconds, that'll give us 5 waveforms. So let's go 0.5. That's good. And then we'll do a calculation, maximum step size, or minimum step size, we'll do 1 micro. So that gives it the resolution. That's how it'll do a calculation every 1 microsecond out to 0.5. Okay, so apply. Okay.
All right.
Okay, let's see if we can run this thing. Let's see, something should pop up at the bottom. Okay, that's good. So trace. Add trace. And let's get rid of the currents and the power in the middle there. Okay, so we want U1 out. Scroll down. That's going to be our output. Are U3, is it called U3 out? I can't read it. It's very tiny.
That says U3 out, yeah.
Okay. And our signal source, was that V5? Yeah. Click on
I
that
think so.
one. Click on
Okay.
U1 out. And then we want the signal source, the positive of that. Let's take a quick look at that again.
Is it V plus right here?
Let's look at your schematic.
Oh, okay.
It is, oh, it's behind that current. See all those currents popped up? Here,
Yeah,
let's shut those off.
there we
Okay,
go.
it's V2 plus is what we want. Oh, but before we leave this, okay, all your bias voltages popped up. And then what you see there is that we got 2.5 volts, 2.5 volts, 2.5 volts all the way to the output. Like if we were to short C1, those would all go to, like, they just get pulled to the rail. But anyway, that's our DC offset that we're going to write on. So
Okay.
let's look at C2 V2 plus.
V2 plus, okay.
Yeah. Okay, press OK. Okay, good. Now let me hold on a second. Let me look at our participants. Has anybody joined that needs to record that I didn't give permission to record? A lot of people joined late.
Can I take this time to screenshot my stuff?
Oh, yes, do that. I'm going down the list. Multi-pin, allow to record. Yeah, we got all the late comers here. We got to okay. I think we're doing okay. Speak up if you want to record. Okay, so you had a chance to snip that and paste that into a Word?
Yes.
Okay, yeah, go ahead. If you need more time, that's fine.
I think I'm good. It was just that schematic for now, right? Where you need to
Yes.
analyze this. Okay.
Yeah. So let's put a cursor on there. Trace, go to trace, and then cursor display. And it'll come out to you. Yeah. So let's put it first at the, we can put it at the valley there. So the input and output are skewed just slightly. Put it at the very lowest point. Now it's very tiny on my screen, but I'm gonna write down, you're gonna read it for me. And I'm gonna write down, let me get a scratch pad. Okay, so on the red one, that's your input signal. What's that say? Minus,
Minus 49.978 M.
okay, so that's essentially minus 50 millivolts.
Okay.
Okay. And then the other one says what? The green one says,
31.416 U.
maybe we're looking at the wrong one. Just above where
Oh.
it says 45. What's it say?
Oh, my bad. Okay. Yeah, 905.906 M.
Okay, so it's just under 1 volt. It's 906.916 volts or
Okay.
906 volts. Okay, good. And now let's go to the apex, the top of the sinusoid. Okay, and then what does that say for the green one?
It says 4.0925.
Okay, so we have essentially between the peak and the valley, we have 4.09 minus 0.906. So we have 3.18 volts. And then if you look at the peak of the red, I think it's going to be essentially 50 millivolts again, right?
Right. It says 50.M. Yeah.
Yeah. So we have a difference in the green of 3.18 volts, and we have 0.1 volts peak to peak at the input. So our gain is 3.18 divided by 0.1, so it's 31.8. So that's spot on where we want it with that resistor ratio. Okay, is that clear? Anybody have any questions? So what we also see here is the signal is riding on 2.5 volts. Actually, we'll put a little more resolution. Let's go to the left on the scale and let's double click on the scale of the numbers there. And let's just put it, we'll make the resolution. Again, it's very tiny on the screen, but let's make it the Y grid. Let's make it, get rid of automatic and make it 0.5. And then we'll see that the thing's oscillating right at 0.5. Okay. Or I'm sorry, I said oscillating at 0.5. It's oscillating at 2.5, which is where we want it. No, we're good. We're all good.
Oh, okay. So
yeah, why don't you capture that? And then in your report, we'll type and we'll write in the peak to peak voltage of the output signal is 3.18 and my input signal is 0.1, so my gain is 3.18 divided by 0.1.
Should I take screenshots of both at the valley and the peak?
No, just the peak's fine.
Okay.
So yeah, screenshot that and then we'll write in the text as what your gain calculation is. And if you want to take some time and paste this in Word, that's okay.
All right. I'm ready.
Okay, good. So while we're here, let's just see where our dynamic range is. So let's change our peak to peak input. Instead of 50 millivolts on our schematic, let's make it 100 millivolts. So then we'll have 200 millivolts peak to peak at the input. And then that's going to try to, with a gain of 30, that's going to try to get plus or minus 6. But what that's going to do is it's going to show us where the thing saturates. So let's just go and change that to 100 millivolts. So again, that's volts peak. So if we go 100 millivolts, we're gonna have a 200 millivolts peak to peak.
Okay.
Okay, good. And let's run it and we'll just see where the thing saturates. Oh, we gotta do trace first. We'll just do
Oh,
we can just
there
look
we
at
go.
U6 out.
U6 out.
Or no,
Or
you
U3.
whatever, you whatever
Yeah.
that was. Was it U1 out?
It's for me, it says U3 out
Oh, okay, good.
and then V2 plus.
Yeah, your screen's so tiny, it's hard for me to see. Okay, so
Yeah,
there we
sorry about
see
that.
it can't get all the way up to 5 volts. It goes up to like 4.6. And then in the negative direction, it goes to it's about 0.6, 0.8. No, let's see, that's 0.5. Oh, no, I'm sorry. It goes up, that's 4.5.
Yeah,
So it
around
gets within
4.5.
0.4 volts, it looks like, of either supply. Now, when we actually build this, we'll see that it's not going to perform. These models in Spice are actually do much better than the actual circuits. But anyway, what we just did there, let me just look at the instructions here again. So the schematic with all the voltages entered on it, that was step 5.
Okay.
And this is actually what I just had you do here is actually extraneous. They want us to do a DC sweep, which will show us something very similar. But yeah, capture this right now.
Should I put a cursor anywhere or?
No, it's not really important. You just well, you can put it at the top. Put that at the top of the plateau. Yeah.
Okay.
And that just will tell you how close you're getting to your 5-volt supply. So are you actually pasting into Word?
Yes, I am.
Okay, so let's just write a note. Let's call this this plot transient showing the saturation levels or the dynamic range.
Okay.
Transient response showing the dynamic range.
And you said this part was extraneous, right?
Yeah, I don't think it says specifically that we do that. I think in the DC sweep that we're going to do next, we'll see that as well. That's, what we're basically trying to do is characterize the dynamic range, really. Yeah, how far we can get to the close to the supplies. And if we have a higher supply, we'd have more dynamic range. If we had a lower supply, we'd have less dynamic range.
Okay.
Okay, so what we just did there was actually part of, let me see. Yeah, we actually did this whole transient simulation was part of step 7. So I kind of jumped ahead when I had you do that. I like to run the transient though for 2 reasons. It shows me all the bias voltages. And then secondly, rather than doing a DC sweep first, I like to look at the signals. It tells me what my amplifier is doing and how it's working. Okay, so I hope that's not confusing. When we ran the transient, that's actually the part of step 7. So now we'll run a quick DC sweep and then we'll run an AC sweep and then we'll essentially be done.
Okay.
Okay, so are you ready?
Yes.
Okay, so let's go back to our schematic and we'll leave it as it is. Oh, no, actually we're going to have to make a change because we're going to keep our 5-volt supply, but we want to sweep the voltage, the reference voltage. So I think what we're gonna do, where you have R3 right now on that divider, we're gonna
Mhm.
cut that vertical wire to the left of it, and we're gonna put a battery in there.
Okay.
Okay, so you can get that whole wire at the top and stuff. You can kill those two for now.
Oh,
Yeah,
okay.
yeah, and that one there. Okay. Okay, so now let's get a VDC.
Okay.
Okay, and let's put it down towards the ground. Go down. It's going to connect. Yeah, right. That's a good spot. Okay, and now we'll connect it to there. Yep.
All right.
Hold on a second. Okay. So let's give that a value of, we want to sweep between 0 and 5. So let's give that a value of 10. Because we're dividing it in half. So that'll give us a sweep. Okay, so let's set up a DC sweep now.
Should I keep the same amplitude right here for the?
Yeah, I think that can stay for now.
Okay.
We'll see. We'll see what the results look like. I believe it can stay. Okay, so we're going to do a DC sweep. And we're going to make the source is going to be V3 to the right. Yep. And we'll start at 0 volts and we'll go to 10 volts. And we'll use 0.1 volt increments.
Should I put the units or it's okay?
No, that's okay. That's okay.
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 Applied.
Let's run that and then we'll look at U1 out and V3. And then we'll look at V3 plus. And also, is there? It's actually U3 in yours, right? Is there
Yes.
is there like a U3 plus in there anywhere? The pin 3, the U3 plus. Is that
There's
it?
there's a U3 V plus. Yeah.
Let's try that one as well.
Okay. So like U3 out and a U3 or V3 plus and then a U3 V plus.
Yeah, let's
Okay.
do those. Okay. The blue one, is that U3 plus? Okay. Okay, so on the scale to the left, yeah, I don't know why U3 plus is flatline. I expected it to have a curve too. Anyway, on the scale to the left, let's adjust that scale because we sweeped up to 10 volts, but we don't need to look that high. Let's go to actually go to Y-axis.
Okay.
And let's go to user defined and go to 0 to 5. Okay, so what we see here is the V3 plus isn't so important to us. It's yeah, what we see here is that the voltage there is tracking. See, actually, I expected to see U3 plus lay over that green line, but anyway, what we see is it's tracking, and then we get up to like 4.6 volts, and it flattens, and then at on the opposite side at 0.6 volts, it's flat until you get above that. So basically, again, what that's showing is the dynamic range of the amplifier. And I don't know if you remember, like we looked at a schematic, I think in the previous lab, of the internal circuitry of an op amp. And so there's bias circuitry that controls the current and controls the load. And so on the bottom there, that's the bias circuitry controlling the load. You can't go all the way to 0 volts. It's you run into the bias conditions of the circuitry. And then on the high end, you got the current they call them current mirrors internally. And those have to be biased on, and so you don't get all the way up to 5 volts on your output. Okay, so that's, you can just label that DC sweep. That was step number 6.
Okay.
So in your report, you can note where the amplifier saturates. You could use this or even the transient. And then when we test it next week, you can compare that to what you actually measure.
So this was the DC sweep, correct?
Yes,
Okay.
it was step 6.
All right.
Okay, so now the last step, we'll do a AC sweep. So let's go back to our schematic.
Oh, do I need to put a cursor on this too, or is that fine?
No, that's fine. You can read pretty much directly
Okay.
where the saturations are.
Mhm. Okay.
Okay, so let's get rid of our V sign and we'll put in a VAC. So V2 will switch out. Yeah.
VAC.
Okay, so this has a constant 1 volt. We don't have to make any adjustment there. It's going to sweep up whatever frequency band we decide, and that's all good. So let's set up the AC sweep. Okay, AC sweep, good. And we'll start at 1 hertz. By the way, I think if you try to start at 0 hertz, Spice has a problem. So we'll try at 1. You don't even have to write out hertz.
Oh, okay.
Okay, and then let's go to 10,000 hertz. And let's do 30 points per decade.
All right.
Okay, let's apply that. Okay. Okay, good. So I think we can run this.
And then the same things
Just
again.
U out. That's all we have to look at there. Yeah.
Oh, which one? U3 out?
Yeah, U3 out.
Okay, that's it.
Yeah.
Oh,
Okay. Actually, can we look at your schematic again? Oh. You know what? I had you. Let's change V3 to 5 volts or go back to our old configuration. Because yeah, we got that thing riding. Yeah, let's make that 5 volts. Yeah, okay. Let's run that again. And then yeah, we only have to look at U3 out. We don't have the inputs 1 volt in. Okay. Okay,
there we
good.
go.
So here's your frequency response. So it says like 30. Yeah, so that's your gain when it levels out. It's like 32, right?
Yeah, 32.
Yeah, okay, good. Okay, so now if we want to find the 3 dB point, we'll put a cursor on there. And 32 times 0.707 equals, let me do that again. 32 times 0.707 equals 22.6. So move to the left to where horizontally you're at around 22. So go quite a bit more to the left. Keep going, keep going. I think I see 20. Yeah, you got to go much more to the left.
I'm at 21 right now.
Oh, you are? Oh, okay.
Yeah.
Are you sure?
Or where am I looking at?
You're
Which
looking at
X5?
frequency. Let's look at
Oh,
you look at the green one. Let's look at the green.
okay.
So you're getting close. I can barely read the numbers on there.
There,
Okay,
the
perfect.
green one says 22
Okay,
right
good.
there.
And while we're at it, let's double click on the horizontal axis on the bottom and make it look like a logarithmic sweep. So click on any one of those numbers. Oh,
Oops. I'm gonna do that. 22. Takes a bit.
yeah.
There we go.
Okay.
It's clicked.
Yeah, let's click on those. And let's go to X grid, get rid of automatic. And then go to the right there. There's 10. It's 2. Yeah, that's the one. Okay, press OK. Okay, so there, that just a logarithmic scale shows up. Okay, so that's your 3dB corner, and it says what, 6 point something hertz?
Yeah, 6.94.
Okay. I think in the pre-lab, I don't have the note in front of me right now, but I think I have like 7.2. So close enough for me. So anyway, that's the combination of the input resistor R1 and the 10 microfarad cap is what's determining that cutoff frequency. And you can see, so it behaves as a high pass. So, you know, at frequencies below 10 hertz, you're probably, like say it's an audio amplifier, you're probably not going to hear anything. If you had to hear, I'm not even sure if human ears, how we do with frequencies below 10 hertz. I think if we have like really good hearing, we can hear up to 20 kilohertz. And we're doing good up to 10. I think this probably can take us up to the high frequencies. But if you did need frequencies lower than that, you'd have to use a bigger cap for C1. Like if you used 100 microfarads, it would shift that a whole decade to the left. So rather than 6.9, it would be like 0.69 hertz is where the 3dB would be. But anyway, it behaves like a, here on this end, it's like a high pass. And if we plot the out to like a megahertz and stuff, we'll see that the thing rolls off. It basically, the amplifier is like a bandpass filter. So you can capture that.
And is that the last parts to do, or is there
Yeah,
more?
today that's the last part. Next week we'll build.
Oh, okay.
And let's see, while I'm talking, the following week we're going to start the diode lab. And I'm going to be out of town. So I'm thinking what I'm going to do is probably record it and send it out through Moodle if I can. Or if not, I'll have to get more creative and post it on YouTube or whatever. And then send you guys a link to do the simulation for the diodes. It's pretty straightforward, but the circuit, it's not really a practical circuit. So it will be beneficial if I give some description of what's going on with the circuit at the beginning. But anyway, on the 5th, I won't be hosting a session. You'll do the simulations independently. And then the following week when I'm back, we'll build the circuit and the diode circuit and test it. Okay, any questions?
Real quick, it was just the AC sweep, correct?
Yes, AC sweep. That was
Okay.
step 7. And if you read the instructions on step 7, it first asks for the AC sweep, and then it asks to run a transient, which we already did.
That was the one of the dynamic range, right?
Yes.
Okay.
Okay, so then next week it will build the circuit. Let's see, there's 8, 9. There's 12 steps. There's 13 steps, but the 13th step is kind of nonsense. It's kind of a trick question thing. It's basically saying, okay, if we remove the cap C1, can you get your circuit to work? And the answer is no. Once you take C1 out, that DC current and DC voltage will be submitted to the gain of those two resistors. So if we have 2.5 volt reference times a gain of 32, it's gonna try to go to 80 volts and it certainly can't do that because we only have a 5-volt supply. So anyway, there's basically the no nonsense steps of the lab are gonna be 8 through 12. So that's pretty short. So next week should go pretty good as well. Okay, I think we're done today. Anybody have any questions or anything you want me to address? Okay, well, thanks, Christian, for running the P Spice and giving Amir a break.
No problem.
And I think we're ready to end. Are you guys ready to end the meeting?
Yes, sir. Thanks, Professor.
Okay, thank you.
Have a good night, boss.
Thanks, everybody. Okay, see you. Bye.